screen as well. Hope my screen visible. Hope my screen visible and my audio also audible to everyone. Just please confirm me. Thank you, sir. So welcome back, and from today onwards, we'll be going to learn on LLM part. So those few are pending. I'll be taking some time and I'll be completing those pending things. Don't worry about the pending things. Cool. So as we discussed in the last class, so we'll be starting with the intro with our LLM and why we need it. Because the industry is completely using LLM. So this is the first layer where AI is working in modern era. So do we have LLMs in previously as well? Yes, from 1950. From 1950 we have AI. Okay. From 1950, do we have log language models? Yes, we do have models, but I couldn't say that it is a log language model. There are models which are trained on some amount of data only. So pre-trained, okay? They only trained up to 50K or uh, some part of data only from the articles, websites, and some other documents internally in the company. And I would say that from 1950s, from 1950 to 1980, so actually there's a kind of rule-based thing. So we know that rule-based AI, right? So this rule-based AIs and rule-based thing, example, you are writing some grammar, okay? So to auto-correct that, we need a kind of a grammar corrections. So language is very irregular at that time, 1915 and 18. Example, we say bank as river bank as money bank account. Similar like that, we have different words. So and it is irregular that time. In order to do a kind of a corrections between the two words, like two meaningful words. So one word, two meanings. Similar way, if I write one sentence, two meanings. So there is a language and word dependencies are there. So in that case, this rule-based things got failed. It is not that so accurate. When you go back and see in this era of 1918, 88, 85 and 1991 also, 90s also. So we don't have such kind of things which is like Grammarly, okay? Those kind of applications was not there to do giving. So everything will be the rule based thing. If it is setting into the rule or this proper input is fit into the rule, then it will do that correction. But even because of the two distinct differences and the dependencies, this AI got failed at that time. By considering this problem, the evaluation of computers. So evaluation of computer means we are making computers to understand in more intellectual way. That is only the goal. We wanted to understand the more computers in more understandable way, understanding the languages, making computers more understanding and different wide scope of languages like this. Okay. So in this process from 1950s to 1980s, we have this kind of problem. From again 1990s, from again 1990s, so there was NLP came. I would say statistical NLP. Again, this is some part of problem it solved. How? Actually, like n-grams it used, like in a grammatical side, it is using a count of words, frequencies. Okay, so it is some part better understanding about the problem. It is some part a good understanding than this this problem. And then we have neural. I guess this is from 2000 or 2003. From 2003, we have neural LMs. So this neural LMS, like I would say, natural language model only. What it will be doing, this is the first time in 2023 they invited a kind of, it's like a vector only. So this word becoming a vector, but this is not that much accurate. It's a vector, but it's not that much accurate. I'll come to the what is vector also and how this is going to be worked. So this is a kind of a vector in the first time, but it is not accurate and too slow. That is a problem in 2000 and 2003. Okay, so biggest identified bottlenecks on AI, uh, before we go into called as the log language models. So I couldn't call long language models in 1950s, 1990s, and 2000 also. I would say that making computers to understand. Okay, so the evaluation of the computers for the understanding. Then later, from 2013, who are working on this data science side from 2013, they would have more context than me, because 2013 we got word to wake like this. So word to wake, that means we have two three words, then each word we will be fixing as a vector, whatever the context, forget about the context, we are fixing as a vector. So one vector, regardless of any context, started from the 2013. Actually from 2010 and 2013, it's actually took the place from the 2013. And then from 2015 to 2017, I would say from 2017 actually LLMs are matter. Now anyone ask you from what is the birth date of LLM or a birth year of LLM, or when would people are calling LLMs log language models, you could say from 2017. From 2017 things are got changed, the development got changed completely on the LLMs from 2015, and things are happen, and finally at 2017 we got what, transformers. In between of this 2015 and 2017, we have called this deep learning things RNN and LSTM things. Just a minute. Okay, this, what this will be doing, this RNN and LSTM, these are nothing but again sequential. These are nothing but again sequential. To make you more easy to understand, I'll tell you one thing. Why this LLM has to come to transformer architectures? Why it has to come to transformer architectures? Only one answer you could say. So previously, we have this system, AI system, to read left to right. I have some sort of word. I cooked a curry like this. Okay. So it is reading from left to right. The sequentially you are reading from left to right, and you go for the second, like forward slash and n, that means you're coming to the next line, and then you're forgetting the first one. You're forgetting the first one. So this is a kind of thing which is LLM is having a biggest drawback. Should not forget. That means, let's say I used I. I means me only. Okay. Or I say it. I cooked it. it means something. Okay, it means, let's say, a curry. So this first line has done. When I go to the second line, I again used it. So this time my LLM or my model is not remembering this it means what. It means is again considering it as new. It means is actually curry. It means actually curry. So when you are reading first para and second para, you're eventually forgetting the first one. From the second side, again you are considering everything as a new, fresh. So that is the biggest problem in your LLM when the transformer architectures came, and this is got solved from 2017. Every LLM is transformer based architectures only. So that is the history of the LLMs, I would say. So that is the history of the LLMs. So the main answer in the LLMs is it use a parallel process. The same thing which I have said will be applied here. A parallel process. So single process we have and parallel process we have. Single process is something that you are reading left to right. Eventually you are remembering, but you are going in a sequence way like RNN. You're going in a sequence way. So if you are going in long text, okay, for short text, okay, it will be remembered. But when you're going for long text, gone. So this is a one more problem on your thing. So when you do parallel process, because of this deep learning, so deep learning means what? It will have every layer that will understand, right? It will have every layer that will understand. Example, if I have a picture like, so this is a dog picture. So this is a dog picture. So in this dog picture, the first layer will be identified like this is one layer will be identified. This is the edge. One layer will identify this is the ear. One layer identify this is the eye. One layer will identify this is surface. One layer identify it is a leg. So like this, all this will be combined and tell you that it is a dog. It is a dog. So like this, in your neural networks, everything will be works as a layer wise, and they'll connect and they'll come to a decision that this is a dog, because the training data is like that. So this is how LLM could understand. So every computer will not directly understand the words. Everything is numbers. Everything is numbers actually. So when your large language models are running, your neural networks are trained on the uh, data, and it will generate the new token. So I'll come to that point. What is the token, sequence, weights, everything. So if you see in this modern days, you are listening about Claude, Opus, Sonnet, ChatGPT 5.3, 5.2, GPT-4, GPT-2 in previously, DeepSeek. Okay, so these are all the LLMs. They are trained on millions of the parameters and the data. So 13 trillions of the parameters like ChatGPT. So trillions of data parameters it got trained. So because of that, it have a very good context and very good new generation token in the next what you have asked. So to understand that in more deeper, let me tell you um like what does mean by the LLM. Okay, so I guess this is an LLM process, the behind case, but in more summarization pattern, LLM means it works behind neural networks only, which will predict on next token. Simple. Your answer should be very simple. In this sequence, LLM means it behind the case, be under the wood, it will work neural networks. It will try to predict the next token in a sequence, which is already trained on billions of parameters. Billions of parameters. I would like to add weights. I'll come to this. What is weight means? Okay. We have. One more thing. When I say it trained on billions of the parameter and weights, that means that will encode or compress the knowledge. Compressed knowledge. Compressed knowledge from your training data. From your training data. So this is what actual real-time definition you could say. You can say. What is an LLM? If anybody asks. Okay. So by using this transformer architecture, it will process all tokens. Okay. All tokens parallel, and there is a main thing called attention. So we have attention mechanism. That is a main thing in LLM, attention mechanism. So this is a real a natural definition that you can say. Don't give this Google answers and all. LLM means it is trained or something data, pre-trained data, trained on the billion parameters. It works. No, it is under the hood. It will work on neural networks, predict the next token in a sequence, and which is already trained on billion parameters of the weights. That is nothing but compressed knowledge from your training data. Okay, and how it will be working on transformer architectures. With that, it will process all the token in parallel, which is not the main point which will be using by this LLM is attention mechanism. So this is the main thing I would say about the LLM actually. Okay, and when you talk about the LLM, there are few things that we need to learn in deep. Then only we can understand how does this LLMs are working. So when we know about these things, it is working. However, we are not the developers. We'll be ultimately going to use them, and we'll do some time fine tuning. If you are a data science engineer, it's your job. Sometimes you have to develop and train and fine tune it. Okay. So example, the main core problem in LLM is attention, which I say attention mechanism. So attention mechanism came and it solved a very good bottleneck. A very good bottleneck. That means every LLM is having surface level knowledge or surface level understanding, I would say. Not knowledge. These words are very, when you say knowledge and understanding, two different things. So every LLM is having surface level understanding. But the problem when your words are very relevant. Example, database database stores data. Just think about it. Database stores data. How much these two words are very relevant. Okay. So this is where your LLM is only having a surface level knowledge, but it is not working properly. It is referring to something. Okay, so that's why there is a called vector. So whenever you LLM is having a sequence life cycle. When you give input your prompt, it will come with the layer wise layer. Okay, so when it will take convert tokenization, embeddings, attention, like this, it will come like this. Okay, in your vector, there's a very important thing is queue. What does mean by queue? Queue is nothing but it will understand what I am looking for. Okay, example, you are searching for something. No, you are searching for what? You are searching for what? Q means query. Q means query. Q means query. And the next thing we have is K. What does mean by K? K means key. K means key. So this key, so when you are input something, it will understand that what I am looking for, and then what do I have it? What do I have? Or what do I have contain? Like this. So this is the K means, that is the key, nothing but what do you have. Example, when you are searching anything from your application in the Amazon, you are searching for a product, TV, mobile, or anything random product name. It will take that, and behind the case it will do a query. Then it will, what it will perform? It will perform search index, right? What? Search index. Search index it will perform. So it is something like that only. Okay, it is a search index. And then we have value. Value means what? V. QKV. QKV. Here it will decide what should I pass info. After your search index was done, you will get some information, right? You need to advertise that, or you need to send. Sorry, this one will be the advertise, and this one will be the sent info. What you should send the information which you got and which is the best match for it. So this is the main formula which this attention, self attention mechanism works. This is how the attention mechanism will work. Okay, and we do have multi-head attention as well, because this is the only single thing is not enough in right now modern LLMs. Okay, so there are some formulas actually. So how this works under the behind the scene, I would say KQE matrices will be understand by the embeddings. I will come to the embeddings, tokens. Now we are discussing about the attention. Okay, in each layer wise layer, if you first understand the self attention, attention means what? Whenever you send any input, whenever you send any input, it will take that input, then it will do this kind of performance behind the scene. What I am looking for, what do I have, or what do I have contain, and what should I pass. Okay, and this is the self attention. and we have multi-head attention as well. Okay, so multi-head attention is like you have head 1, head 2, head 3, head 3, like this. So what happens here, the problem with the single attention is it will only capture one type of relationship only between your, when you are mapping those things. There's a deep engineering in it. So when they are mapping, it will be only one type of relationship only. But when you come to the multi-head attention, it's something like, I would say, n-type attention. Okay, n-type attention. So it will be doing compute in parallel process. In parallel process. So to understand this, there is a formula actually. We don't need much, we won't do anything. It is just for our understanding. So WQ, WK and W WQKV something. So I forgot. Uh, Attention KQV. QKV, WK, WQ, WV. So it's a block for performs. Again, I'll tell you about the blocks also to actually understand from the blocks. So QKV is a mechanism in propagation. Q is a linear propagation. WQ means that is the input. K means linear projection, WK input, and WV, it is also input. There's a layer input, hidden layer, output layer. Input, hidden, output. This is how it will work actually. Okay. So what happens in this multi-head attention? Okay. Example, example, in your head 1, in your head 1, it will go for the subject and verb from your language. That means it will do some sort of agreement. That means a synthetic relationship it will find. And in head 2, it will go for resolution. That means the word is looking for which reference. It is a curry, or it is an animal, or it is I, something like that. Head 3 will understand the distance between the relationships. That means nearby word. Nearby word. This is just understanding, we are not doing anything. It is we are learning how it will work. We are not doing any changes or any code developments here. Please keep it in mind. So I'm just telling how this is will work. Let's say we have something other head again. It will understand the concepts, and head 5 will be understanding the modifying the clause or modifying the words, something like that. So up to n head it will work. N head it will work until you get a proper view. So this is what multi-head attention is. GPT GPT-3. I think GPT-3, when I see last time 96 heads it will use GPT-3, and GPT-4 use, when I see last time 128, I guess. Parameter count, no. Yeah, n head number of, so use 128 when I see some last published article was 128 heads. Okay, so each head will be having its own view, its own content, its own uh, sequence of output actually. So all those sequence will call concatenated, means we everything will be include and concat them and project as one and project as one. Okay, so that is how your GPT-3, GPT-4, these things are working. So when you upload any image, when you ask a big prompt, when you're asking code to write, suggest something, so it will be using behind the case is like head attention, multi-head attention, multi-head attention. So for this, there are some formulas are there. I have not prepared any notes right now. I'll give with formula how exactly it will be. Okay, for this class. So this is how LLMs will be working with the attention. Okay, and coming to the tokenization. Tokenization. So tokenization, what happens? Not correct word. Hmm. Tokenization. Tokenization means whenever you are communicating with any LLM will determine what it will struggle for to give you the best performance actually. Okay, so in that tokenization will be help in that to understand the words, to understand the words to the LLM side. So before this, what happens? It will be embeddings. So better we will discuss about the embeddings. Okay, embedding means embeddings. Embeddings. Right. Let's keep it this somewhere. Yeah, embeddings. So embeddings, what happens when I write any word like king or apple or Rajni, something like this. Computer won't understand direct word. Just a minute. Just give me a minute. Sorry. Some important call from the office. Okay. Where we are embeddings. Let's say I have a word like this. What it can be anything. The word can be anything. King, apple, Rajni, or computer, or you would say banana or something. So your computer will not be understand directly that word. So computer will only understand numbers. So this is an embedding that will do this process, understanding the word and converting into the numbers. Converting into the numbers. Like the list of numbers again, you should mention the word 0.2, okay, comma 0.8. So every word is having a number. Okay, your embedding will do that actually. 0.1, like this. The list of numbers, the list of numbers, so it will write this is nothing but embeddings. Okay. Then all these embeddings, so all this collection of embeddings will be going to store in vectors. And now what is mean by vector? It is mean by a vector. Vector is again the whatever the number of the list numbers of the list which is has done. So in this, it is going to coordinate and map. It will coordinate and map 2D. 2D map or 2D we can say. 2D means like we need two numbers. Okay, one is x and one is y. One is x, one is y. In between, we need to locate one point. Okay, so in this is again comes from the deep learning. So in the deep learning, we use hundreds of thousands of concepts like numbers. So we will trying to find high dimensional space. Okay, so that is nothing but the vector. Vector is nothing but vector is nothing but a mean, a mean where it will represent a point by the list of numbers. By the list of numbers. Mean representing a space point by the list of numbers. So that is what vector means. And there are very good tools are there outside in the market. So vector databases we say. So vector will be used in search, recommendation, RAG engine systems. We use vector effectively. It's very important in your organizations. Okay. So that is vector means we have ChromaDB, we have VV8, we have uh, Pisa, and we have PG vector, we have Pinecone. So these are all the popular vector databases. And for this embeddings, we have Word2Vec, which is from the Google. We have Glowy, we have Stanford, we have FastTech from Meta, we have OpenAI embeddings, which is very popular. We have Amazon Titan embeddings from the Bedrock, which is very popular, and we have BERT as well. So this is everyone know. BERT, SBERT, BERT, sentence BERT. Mostly we use in AML. Sometimes you no need to directly use AI, LLM directly. You can even done with your ML only. So in that case, you can use BERT thing. Okay, it will convert entire sentence into a single vector, into a single vector. Okay, with a semantic search. So there is a one score for semantic score. We will see all those in detail just to make you understand about this word's definition so we can align one after other easily. Okay, so this is how we would be using these things. Okay, and so for the LLMs, for the LLMs, for the transformers, we have encoders. I said right, encoding compressed data. Okay, encoders only transformers, decoders only transformers. This is something I have missed. I need to tell you about this. Transformers. So when I say transformers, so we have types. Types. Types are nothing but again encoder only transformer. Okay. Decoder only transformer, and we have encoder, decoder. Okay, transformer, and we have vision transformer. We have other more also, but some transformer. Okay, what is this? This is, it's only understanding the text. It's only understanding the text. This is used by Microsoft. Uh, like we have dbert, Microsoft. There is a Google also using BERT. Meta also using Robert. So these are all the encoder only transformers right now, because it do a very great classification, NER, sentiment analysis, NNA, summarization. So all these things can be done at high level at good extent on this. So if anyone working on LNP stack, they know what is NNA, NER, one more also there, NND or something. So that will be can done on this encoders only transformers. Okay, that means you give it text, it will understand in deep, actually in the from the roots. Okay, so coming to the decoder only transformer, so it is nothing but generating text, GPT-1, GPT-2, GPT-3, GPT-4 from complete OpenAI. This will be used. OpenAI is using this one, sorry. Okay, Anthropic is using this one. Your llama, llama 1, llama 2, 3, Meta, Mistral, Falcon, all these are using decoder only transformer. So it will generate the next token, next text, next text by token, next text by a token. So example, your chatbots. Now coming to this one. So encoder and decoder, it will be like this: input plus output, input plus output, like text to text transformer, transformer, but but there is one more also called Marian Matty something, yeah, Marian MT something like that. Okay, so which is very good at translation, your language translation. Your chat GPT is doing translation from English to Hindi, Hindi to Telugu, right? So here it will be used encoder and decoder transformers, summarization. So it will encode and decode into an output text. So that is a very good one. And the last one is WIT, means it is nothing but vision transformers. So Google was also using this. It will, like your DALI also, DALI E is also using this diffusion images understanding. All can be done with your vision transformers. So these are the four types of the transformers that right now in market will be used. Okay, coming to the one which we discussed, tokenization. We left this one. Okay, tokenization means I have a word like Kubernetes. I have a word like this, Kubernetes. If you take any GPT-4 example or Anthropic, GPT-4 or Anthropic will be used tokenizer, called tokenizer. So there are things. So since the machine is not directly understand, it cannot read directly. It has to read from the tokens. Okay, it has to read from the tokens. So what happens? It will be going to do like this. If I open this bracket, cube, netis. like this. It will divide characters, subwords, like this, sentence and all. Okay. When it will divide, by understanding this, it will create a tokens. That means the first cube is nothing but something like 42. I'm taking a random number. The second one is 8678, like this. So your word will be converted like this. Your word will be converted into subwords. Example, running. Okay. Run plus ing. Runner. Run plus ner. Like this. It will convert like this. And then it will put it into this one. Like this. A word. Like this. Okay. Subwords it will do. If you ask in Kubernetes, if you ask in Telugu, Hindi, English, this token count size will be different. See, understand, my dear friends, like in English, it is optimized already. But when you go for any other local languages or state languages like Marathi, okay, or Telugu, Kannada, Tamil, Malayalam, okay, the tokens are will be heavy. It will be more than the actual English, because from the evaluation of the computers, English is the only one thing, right? So we developed everything on the English only, not on the different languages. Now we are trying to make the computers to understand on the different languages, which the tokenizer and tokenization is creating more tokens. So the same message you type in English, it will use less tokens. The same message you type in the Telugu or in a Malayalam, it will take more tokens. That's the difference actually between these two. Okay. So whenever you communicate, even though languages, you write JavaScript, you write Python, you write other code. Okay, how many tokens will be consumed in the behind the case while it is coming on the output? Okay. So again, it depends on the languages. So it will use less tokens, and your operas will be eat lot of tokens to understand, to create a high mode understanding intelligence layer. Similar way, your Sonnet will be very less. Your GPT 5.3 will be in the human mode. It is also using optimized tokens. But when you give Telugu or when you give Tamil to the chat GPT, it is also consuming a more tokens actually. Okay. So for this, all your LLMs are using byte pair BP, byte pair encoding, BPE, which is nothing but byte pair encoding. This is the algorithm behind it will run. Okay. Example. Example, I start one prompt. Okay. So then it will divide into individual 256 byte tokens. And then it will count all bytes pair in training corpus. Corpus means the list of words. Okay, the list of words. Corpus. Context. Okay, the body type, the male body type, the list of words, the para, small para, sentence. Okay, that one. Yes. Okay, and then it will merge most frequent uh, most frequent pairs actually, then it go for the new token. I'll tell you an example on this. I guess you won't understand like this. Example, corpus. Okay, I'll take the corpus. Corpus like um, something like AA, uh, AA, triple A, BD, or AAA, BAC, random words like this. This is the corpus training data. What it will do in first step, it will be like this. It will go A, comma A, comma A, comma B, comma A, comma A, comma A, B, comma A, comma C, like this. And in second, what happens? It will try to pair. It will try to pair. How it will pair? It will pair this 2A, the first two A's, the first two A's as into a Z, like this. So in third step, what happens? It will be like this. Z, Z, A, B, Z, B, comma A, comma C. Right? If you see these two, these two will be converted as Z. Okay, it merged as a pair. And then in next what happens? In next what happens? The fourth step, again it will look for the second next most pair actually. Next most pair. From above, what is again next most pair? ZA. We can take ZA. Okay. Z comma A. I can take it as Y. So what happens in the fifth step? Y, Y, comma B, comma D, comma Y, comma B, comma A, comma C. Like this. So it will go on like that and it will try to pair, and this is how your tokenization will be happens, okay, behind the case, which is worked by the algorithms encoding.
Sorry,
So
Rajani, I think the step 5 I don't understand. So you have one Y for ZA, and then you have B. I don't know where you got D from. And
D,
then you have ZB, which I
no
don't
no
know
no,
how
here
it's converted to.
here you can see triple A is there, right? Triple A is there.
Okay.
So first two A's I converted as Z.
Z, yeah.
Okay, so
Yeah.
then these two A's I made Z,
Z,
and
yeah.
A is same, B is same. Okay, I
Yeah.
have not used this D here. Okay, so and these two
That
A's are
becomes Z.
Z and B AC as usual.
Yeah.
Then from this output, I was telling that Z A as a Y. So
Ah,
this,
okay. Okay.
okay, this
All right.
two as Y,
Yeah.
and B, Z is I didn't took in the next case. You can delete it
Yeah.
here, and Y. Okay, so Z is Z only. Sorry, Z A, right?
Yeah. ZA should be Y, isn't it?
Yeah, so that means Z A is there in Y only, Z also there is Y only, because I merged it, and
Okay.
then Y and B A C. So like
Yes.
this,
Yeah. Okay.
second most. This is how the byte pair encoding will work.
All right. Okay.
Okay, that's why what
Okay.
happens, the biggest bottleneck is LLMs are very bad at arithmetic. So numbers, maths when we give in the starting, because same case I'm working on the words, but when you take 1, 2, 3, 4, 5, 4, 4, 8, 9, 7 like this. So it will convert like this 4, 5, 6. So model will not understand, doesn't see it once the numbers. So LLMs are get confused at that time. That's the most problematic thing in the LLM. But later the problem got solved. So we have tokenizers actually. We have different tokenizers, custom BPs, sentence piece BPs, sentence piece BPs. Like your GPT-4, GPT-4o is using CL100K based BPs actually. So this is the behind the case, like I would say the the underlying process of how this tokenization works. Okay, and now how the things will be happens in your transformer. So in your transformer, the first layer was input text. The first layer was input text, and the second one is tokenizer. Okay, tokenizer ID 9906911737, like this, whatever it is, token IDs. And then what happens? It will go for embeddings, embedding layer. Okay, and then it will go for encoding, like positional encoding, I would say. It's inside the transformer actually. Okay, and there is a transformer blocks. Here the things come transformer blocks. So the blocks are nothing but the first one is like layer norm. I don't remember, but whatever I remember, multi-head, it will come like self-attention multi-head, and then layer norm, MLP, multi-layer thing will come actually. So here, and then connection, something like this. I really not remember this. Transformer inside flow. KB cache, this is this one. Layer normalization, tokens, multi-head, layer normalization, MLP, yeah, feed forward and then normalization. This is how the workflow is. So after this, there is a final layer, and then probability distribution, and then next token. This is how inside the transformer it works. Next token means it will generate the new one. Okay, so token embeddings. Everything will be a token ID map with the vector dimension like D model, NN embeddings. These things can be happen in the PyTorch only. So then it will understand them, it will deploy. So this is how the actual things will work. Coming to LLM life cycle, we understand the very core points of the embeddings, tokenization, these things. So because Without this understanding, we cannot perform any lab on the LLM side. Hope you understand. So the first thing I need to understand the life cycle of the LLM. How happens in the companies? Life cycle. At your companies, how does LLM is choose? Once is chosen, and what is this life cycle of it? Okay. The first one is problem definition. The first one will be the problem definition. What you are looking for. Okay. With that only you will be selecting LLM, right? And data collection. And third one would be data cleaning. We know in MLOps we seen, right? Similar way these steps also. But there we call feature engineering, those things. But no, here you can directly say data collection and data cleaning. And then tokenization. And then pre-training. You need to do this pre-training. And then you have to do fine tuning. And then we have to do alignment. Alignment is again nothing but something called RLHF, HSF, like this. It's in a pipeline. These things are in a pipeline, and it's a pre-training pipeline only. We'll see this SHFS and RLHSFS. So these things, and then you do evaluation, and then next we'll do optimization. And if I'm not wrong, after optimization we will deployment, and after that we will do inference test like drill test or infer test, performance test. With that we will decide our NLP. All this will be done here, and then we'll be using monitoring, and then feedback loop, and then retraining. So this is the entire life cycle of an LLM project. This is an entire life cycle of an LLM project actually. Okay, so this is how we have to build again. So fine tuning, when you do this fine tuning, that means when we are running training on a model, we give set of Q&A answers. So what cake I have to cook, a kind of instructions I will provide here in this SFT. So when I say RLHS, RLHF, that means reinforced learning, feedback, human feedback something. Okay. So that means human will rank something. Humans will do ranking. Okay. Does it harm, honest, what sort of it is? We do ranking on it. So that is what RLHF. This is again from your three stages of the pipeline. We call the training pipeline for your LLM. Again, we add some domain knowledge, those things. It's again an add-ons, but a raw life cycle of an LLM is this is the LLM life cycle. So for today, I'll be just doing this a kind of understanding and how this embeddings, how this tokenizes, all this. Tomorrow we'll be going to see so which are all the uh, this tokenizers are available and embeddings are available like word to wake, fast text or OpenAI embeddings, those things. We'll run some sort of labs on it, and then we'll move gradually towards the LLM practicals. Once we get the good understanding on LLM practicals, let's go with the bedrock agentic core, or with our at least with our Python systems, uh, or LLaMA or LLaMA, something like that. We will take and we'll start with LLM configuring and deploying them and utilizing at the application side. So we need to learn in a distributed way, not in a one way angle, like what is an LLM, like how MLOps we learned from the problem specific point of view. This is a problem, we are developing a model, deploying, configuring the pipelines, right, from the different SageMaker side, machine learning workspace side, and data collection part. How we have seen similar way, we'll also see for the LLMs. We have a lot of add-ons here. Okay, we have knowledge base add-on, RAG add-on. So these things, vector databases, we need to add on to it. So ultimately, we're going to deploy them in a Kubernetes. Okay, we need to run pipelines for them. We need to deploy this LLM in specific area where you deploy in EC2 or where you deploy in the Kubernetes. We'll see them. Okay. Oh, any doubts as of now? Do you not understanding this LLM concepts, this terminologies, or everyone is good at this? I guess I have already collected one command here. You can see. So pip install token. When you run to the GPT-4 hello world, when you say in Telugu that namaskaram, it's called hello only. How many tokens it will generate? Okay, how many tokens it will generate? So the first one is 2 tokens, but for my Telugu language it is 16. You see, this is how you are eaten by the tokens, and your quota will be done. Your context limit will be over there. So whenever you're using Hopus, Sonnet, if you are using in your company Cloud Code, every company is giving you Cloud Code, Cursor, Copilot. Utilize them properly, because if you are doing a code generation on Java, JavaScripts, Python, or Next.js, any code, understand which the code is generating more tokens. If it is that, then do a routing between the models so that your quota will be not over. If you keep one model and you keep trying hitting generating the code from that single model only, it will eat your usage, especially if you're using Cursor from your company subscription, especially if you're using Anthropic Cloud from your Amazon Bedrock from your company subscription. Done in one day, you'll be done your tokens. So rest of the day, rest and 24 hours, you have to wait to work on it. So don't do, understand the work. Any architecture, any design, or any folder structure, or any new idea that you want to generate, and go for Opus. After it is got generated, since Opus will maintain in memory, then switch back to the Sonnet and do your code generations over there, and then validate with the Opus. But don't tell Opus to write the code. Writing the code outputs could be done with the Sonnet. Again, in Opus also, it will take a lot of input tokens. Understanding, I will understand this much, this much, this much, and it will drain your tokens completely. So, anyone if you're using, just try to use in like in a restricted way, it will give a good output. Any questions so far? And agents also. Your agents, whenever you're developing any agent, you should also concentrate on token. It will be we are burning a lot of money on the providers. No. Okay. So then no, then there is one more new tool called Cairo. Cairo Dev. Anyone tried? It's an agentic platform development enterprise level. Okay. So it is something like it meet up cursor agentic AI development platform. So you can do at your production level also, but not at 100% proved. People are still running the uh, kind of um, prototypings only, not production level. So you can see this similar like your Cloud Opus. You can develop, generate, and deploy them. It is not providing, I guess, a kind of cloud agents what Cursor is providing. It's they claim like it's an autonomous agent, but I've even not tried. This is something very cool in the market. Most of the enterprise people are looking around it. Cairo, Cairo or Cairo. Okay, then. So if no, then I'll come up with the notes. And since I just today back to Hyderabad, I didn't get time to make a notes. I'll do a notes on this class, and then I'll create a labs for tomorrow on the same, and we'll go similar phase with the understanding of LLM in more deeper.
Recording stopped.
Also cover KV caching. Yeah, we will also do KV caching in this one, VLLM. Thank you, everyone.